Okay, so we're going to start 16.6. It's on parametric surfaces. And area. We've, in algebra and in your first semester of calculus, curves were the focus. And curves were always y as some function of x. And that works, but it has limitations. Curves like that have to be functions. And there's this whole thing about vertical line tests and all this stuff. And it turns out you can get away from all of the problems with curves if you parametrize them. So parametrizing curves is more flexible than just writing one variable as a function of the other in x, y coordinates. And same thing turns out to be true for surfaces. We've had lots of surfaces where z was a function of x and y, or sometimes we just describe them implicitly where you have a function of x, y, and z equal to some constant. But now we want to do to surfaces what we had done to parametric curves, where we would describe them in terms of two independent parameters. Curves are described with one independent parameter because the curves are one-dimensional. You need two independent parameters to define a two-dimensional object like a surface. So here we go. Okay, so that's a point on my curve. This is going to be r of uv. So r, the vector r is always a position vector in this class, as I think you probably figured out by now. My screen is frozen, so let's see if I can keep that in view. There we go. So there's my surface. R of uv is my position vector. And it's two-dimensional, meaning if you let, what I think I'll do is sort of, let's say we hold v fixed and let u vary. Then you'll describe motion in one direction like this. I'm going to try that again. Okay, so that's where one variable like v is fixed, so allowing u to vary. And then if we do the opposite and make u fixed, then you could get a different curve, maybe like this. Going down the backside. Okay, so this curve on top is with holding v fixed. And I would say with varying u. So that's just a space curve. Okay. And it's one-dimensional because only one variable, one parameter is being allowed to vary. Okay. And of course, the other case is over here, where we are holding u fixed. With varying v. And we know they're independent parameters if those two curves are different curves. They would cross at one point. But they're independent parameters if those are different curves that they don't have to be perpendicular, but they do have to go off in independent directions and only intersect at a point. Okay. And this RVV is a three-dimensional curve, so I should say a three-dimensional surface. So you've got to have three coordinates. There will be an x function of u and v, a y function of u and v, and a z function of u and v. Okay. Just a real quick, let's just use some quick examples. So for spherical coordinates, I want to remind you the transformation rules. Okay, the x is rho sine phi cos theta. Y is rho sine phi sine theta. And z is rho cos phi. And of course, x squared plus y squared plus z squared is rho squared. On a sphere, rho is a constant. Let's say a sphere of radius a, rho is constant. So the parameterization would have x equal to a sine phi sine theta, y equal to a sine phi cos theta. Oh, I got this backwards. Sorry, guys. X has got to have the cosine, and y has got to have the sine. And z gets an a cos phi. Okay, and that's how you parameterize a sphere. You would need phi to go from 0 to what? Let's see if I can get the chat going here. What would be the limits for phi, guys? Yeah, thanks. Phi has to go from 0 to pi. And theta, as usual, goes 0 to 2 pi. Okay. And that'll sketch out a sphere. Okay, so that's a sphere. And then I want to do an ellipse real quick because ellipses are just like spheres. Okay, so for the ellipse, we could do like x squared over a squared. Sorry, I should say the ellipsoid. X squared over a squared plus y squared over b squared plus z squared over c squared equals 1. Then it's essentially a sphere with 3 different radii. So you could almost just copy everything over for x, y, and z here for the sphere, and just change the radius for each variable. So here's the sphere, but x goes from negative a to a, that's fine. Y goes from negative b to b, so you have to put a b in here for y. And then z goes from negative c to c, so we need to put a c for the z coordinate of each point. And that'll graph out an ellipsoid. Let me do a real quick reminder how that works. Okay, that's a quick kind of a ugly sketch. I didn't think that would go well. One more time. Yeah. That's better. Okay, so that's how you graph an ellipse. How about this one? For any function like z equals f of xy, you could do x is u, y is v, and then z would be f of xy, so that would be f of uv. Okay, so that's an easy way to parameterize the surface. You say r of uv is x, which is u, y, which is v, and z, which is f of uv. So there's your vector function. On the other ones, so for the sphere, you'd have r of uv. Actually, we do theta and phi. So we'll say phi theta is going to be the x coordinate, a sine phi cos theta, y coordinate, a sine phi sine theta, z coordinate, a cos phi. Just like that. Okay, so that's two independent parameters that vary independently of each other, and those points, and that's an infinite number of points that would trace out a sphere. Similar to the ellipse, which I'll zoom in on here for the ellipse. Obviously, the y coordinate needs to have a b, and the z, oops, y coordinate needs a b, the z coordinate needs a c. And so that's the vector function for an ellipse. Okay. Also on the ellipse, you would have, just as before, you'd have phi going from 0 to pi and theta going from 0 to 2 pi. Okay. Any questions? Let's do a cylinder. Okay, so a circular cylinder. Okay, so you just do x squared plus y squared equals a squared. And it seems, because it's a cylinder, it sort of makes sense to put it into cylindrical coordinates. So one thing to remember with a cylinder is that x and y are constrained, but z is not. So you could say x is like r cos theta, and y would be, I shouldn't say r cos theta. Let's do a cos theta because the radius of the cylinder is a. So x would be a cos theta, y would be a sine theta. And then z is unconstrained, so you could just say z is z, okay? So z is just z. So when you write this as a vector function, you'd have an r of theta and z, okay? And x being on the circle would just be a cos theta, and y would be a sine theta, and z would just be z, okay? I don't know that we need to constrain z, but it would make sense to say that theta would be between 0 and 2 pi, but that's not necessarily required. Any questions about the circular cylinder? So most of this is pretty obvious. If you do a cone, let's try that. So a circular cone. So it's been a while, but the cones are x squared plus y squared equals z squared. So we say z squared is x squared plus y squared. And if I stipulate that z is greater than or equal to 0, then I could say that z is just the square root of x squared plus y squared. Okay. Okay, any questions? That's just a function of x and y. And you could say, one parameterization is just that x is x, y is y, and z is the square root of x squared plus y squared. That would work fine. It might be easier to use polar coordinates here as well. So then you would say that x would be r cos theta, and y would be r sine theta. Now we don't want r to be fixed because on a cone, r being the distance from a point to the z-axis will vary on a cone, unlike a cylinder where r is always a, like in the previous example, a being the radius of the circle or cylinder. Okay, but if x is r cos theta and y is r sine theta, then z is the square root of x squared plus y squared, so that's just r. Okay, so this is maybe a cleaner way to parameterize the cone. You would just say r, this is uncomfortable, but we're going to say r of r theta, distinguishing the vector r from the radius r. Yeah, so we could say x is r cos theta, y is r sine theta. Oops. And z would just be r. So that would make a cone. And then again on this, he would stipulate probably that theta would go from 0 to 2 pi. Okay, any questions about that? So there's a handful of surfaces Any questions out there? There's one more that I'm going to do, and then we'll get into the calculus part. Okay. Let's go to a plane. This plane is going to be containing, oops, the point, and I think it works to use r sub 0. It's, remember, points and position vectors are really the same thing. So the point r0, an initial point, and the vectors a and b that are basically a and b have to point in different directions, or it won't work. If they point in the same directions, this plane will not be a plane, it will be a line. Okay, so this is actually super easy. Just very quickly, we'll draw a coordinate system. Okay, and then I'm just going to kind of set a plane out here, just kind of out in space, a plane. Now, this R0 vector is a point in the plane, so this would be our R0 position. Okay. Okay. And then the plane has to contain these two vectors A and B, so I'm going to go ahead and draw an A kind of coming out from that point, A, and then a B just in some other direction, like that. Okay. And basically what you want to do is just recognize that any point in the plane can be found by adding a multiple of A and B to R naught. So basically what we want to say is that R, and this is the parameterization of the plane, R of UV. Okay, we need to set you up in the right position, so we'll start with R0, and then we'll just add multiples of A to multiples of B, and you know that has to be in the plane, and we're just claiming that any point in the plane can be found by picking the right value for U times A plus the right value of V times B, and that would be the equation of that plane. And that's all you need to do. Okay, any questions? I mean, we could do a quick example of this. So just a real quick one here. So give a parameterization. It's really, any surface has an infinite number of parameterizations. Of the plane containing the points. So this is just 2, 3 points out of thin air. And this plane, see, the nice thing is this can be a vertical plane. It can be horizontal. It can have any orientation at all. That's why we like parameterized surfaces, because they don't have the same constraints on when z is a function of x and y or whatever, because there are all these places where z won't be defined sometimes. And that often can be avoided with a parameterized surface. So here are my points. I'm just going to make up 3 points. 2, 1, 3. Let's say 5, 4, 7, and 6, 1, 2. Let's do 6, 2, 3, bad. Okay. So, so basically what I'm seeing is 3 points. 1, 2, 3, like that. And so let's call them P, Q, and R. Okay, to simplify. Okay, so, and it doesn't matter which is which. This could be, first one could be P, second one could be Q, and the third PR. And what I need is a vector. This first one, PQ, would be like my A vector. And PR would be like a B vector. Okay. And P would be my R naught. Okay, so this is the same thing. Okay, so easy as it gets. So let's do A is going to be R, let's say Q minus P. So you'll do 5 minus 2. So 5 minus 2, and then 4 minus 1, and 7 minus 3. Okay, so that's going to be 3, 3, 4. Any questions there? And then B, I guess is going to be R minus B. So that'll be 6 minus 2, 2 minus 1, and 3 minus 3. Okay, so 4, 1, 0. And you can see neither one of these vectors is a multiple of the other, so they're definitely pointing in different directions. Okay, and then again, this R naught is this P point. It doesn't matter which one you use. So, but R novice 2 is 2, 1, 3. And then the plane R of UV will be R naught plus, I think I had said UA plus VB. Like that. So you could say 2, 1, 3 plus U times A, which is 3, 3, 4. And then plus V times 4, 1, 0. And then probably if you wanted to express this as an X, Y, and Z coordinate, then you need to combine these. So it would be 2 plus 3U plus 4V, comma, 1 plus 3U plus 1v, we'll just say v. And finally, 3 plus 4u. Okay, so that's our plane that contains those 3 points. Okay, any questions about that? So it's still, each point is still defined by 2 independent variables. It's just this u and v instead of x and y. And you pick the values of those 2 independent variables, and you get an x, y, and a z. So that's a point on a plane. That's pretty straightforward. Any questions? Okay, now it's time to do a little bit of calculus with this. So let's see what we can come up with. Okay, I think I want to go ahead and grab that original graph that we did, and I'm just going to copy this one down. And I think you can just add to the graph up above. So all I really need to do is show what the tangent vectors look like. So, and these will be partial derivative tangent vectors. Oops. Oh, I don't know. This is really bad because I only have one hand. I don't know if it's going to let me work with just one hand on this. So there we go. Okay, and the idea is that if we hold v fixed with a varying u, the tangent vector, and I'll start at this point of tangency and kind of go down like this, that would be r, again, varying u, that would be ru. Okay. And that's actually, I think I drew that too long. I don't like that. So I'm going to shorten it. I don't know what else to do. Okay, so best I can do. There we go. And then I'll do RV. That's holding U fixed and letting V vary. So I'll get a tangent to the other curve. So this one here I'll call RV. Okay. Okay. And then we're doing surface area. So differentials are always, differentials for surface area tend to be found by doing a cross product of 2 non-parallel tangent vectors. So here come my non-parallel tangent vectors making a parallelogram. Yeah, and this is not going to look great, but we do what we must. Okay, I'm going to shade this in so it sort of looks like a tangent plane. Okay, so that differential area is going to be ds. And what I really need to do is make RU and RV differentials. So let's call this RU du here. And RV dv will be parallel to RV. So again, let's just kind of make this RV dv on the other side. Okay. Okay. And so those two differential vectors, that's like a dr is what we used to do with curves. Dr was just r prime times dt. Well, the parameters are du and dv, so we have to say ru, du, and rv dv, which is just like doing r prime times dt, but in two different directions. So those become our differential vectors. And so ds is going to be ru cross rv times du dv. And notice that's a vector. So this the magnitude of ds is is ds the scalar. Okay, so ds without the vector is the magnitude of ru cross rv du dv. Okay. And so the magnitude of ru cross rv du dv. And let me go ahead and just put the whole thing out here. Hang on, I got to erase something. Okay, so this whole thing is just the differential area ds. And that's what's in the diagram here. And that's a capital S. Lowercase s is reserved for arc length. Okay. And so ds with a vector over it, it basically has the magnitude is the area of the differential parallelogram. But the direction is perpendicular to the surface. All right, any questions about just the definitions here? And again, ds, the scalar, is the magnitude of ds, the vector. Okay. So they're very closely related. It's just that sometimes we need ds to be a vector, and sometimes we need it to be a scalar. And you may remember, usually when we dot a vector with a differential vector, we're doing a projection of one vector onto another. And that's done when we compute work. It's also done when we compute flux. So we need differential vectors for flux. That's a surface integral, which is basically what we're working on right now. Okay, but surface area is just a double integral over a surface, call it S, of ds, the scalar. Okay, so that's the definition of surface area. Okay, now if you wanted, you could expound and say, oh, this is an integral where ds is the magnitude of RU cross RV, like that. And then you do your du, whatever order works best for you. And you just do your limits on U and V here. Any questions yet? Okay, so let's try this real quick. So here's a question for you. Find the area of the surface. This is going to be y equals x squared plus z squared. Inside the cylinder. X squared plus z squared equals 16. Which means radius 4. Okay. So this y equals x squared plus z squared, that's a paraboloid opening along the y-axis. So what you want to do is draw one of these kind of a bullet-shaped paraboloids like this with kind of a circular cross-section here. And then you'd have your y-axis coming out like this. And of course, x over here somehow, and z going up, like that. And I need that maximum radius to be 4 here because I have to stay inside the cylinder. X squared plus z squared equals 16. That's a radius of 4. So I'm going to draw my maximum radius here like this. That is not a good picture. I'm going to try a little harder on this. Okay, and again, my radius here, so I'm going to pull this off. That's a radius of 4 going up there. Oops. I need to know that y coordinate. And that's easy enough. So if z is 4 and x is 0, you can see right, right here x is 0, z is 4. So to know the y-coordinate there, you just put 0 squared plus 4 squared, and so your y-coordinate comes out to be 16. So right here, this point has y equal to 16. Like that. Okay, any questions? Chris is asking me to explain the concept of magnitude area. I think do you mean like a vector area? So the magnitude of the vector area is just area. So a vector area is it's equal to just the absolute value of the area. Okay, well, I could just say area. So vector area is area times a unit normal. Okay. So Chris, all we're doing is you're taking some area in a plane like this, or on a surface, but we're doing a flat version of it. So the area could be A here. And then your unit normal could come up perpendicular like that. Okay. Okay. And so A times N, I would just call an area vector. I can't, I hear what you're saying, and I'm not sure you should hang on to the idea of magnitude area. I think I might have said magnitude. I don't know what I said, but let's not get hung up. What I've just explained to you is what you need to grab onto, and that is that we start treating area sometimes as a vector, where the vector has direction and magnitude. The direction has to be perpendicular to the surface, and the magnitude is the area. Okay, so that's a vector area, and in terms of magnitude area, I don't know what that means even, so you don't need to worry about it. Okay, and if I said it, then it was a mistake. Okay, so anyway, I'm going to tuck this thing away here. I don't know what I'll do with it. Okay, so what I want to do is I want to parameterize this paraboloid here. It makes sense to use polar coordinates, but it would be in the xz plane. So let's use polar in the xz plane. So I guess you would say x is r cos theta, but z would be r. Yeah, that's fine. Z could be r sine theta. Okay. And then y is x squared plus z squared on this surface. Okay. But that would be just r squared, I think. So your parameterization, I think I'm going to use a capital R, just not to confuse it with the lowercase r. So r of little r theta is my surface parameterization. Oops. Okay. So we've already decided that x has to be r cos theta. Okay. Y has to be r squared. Okay. And z has to be r sine theta. Okay. And then you really need, if you're going to find the surface area, you'll need the limits on these variables. So I'm sure that theta would go 0 to 2 pi. Anybody want to take a guess at the limits on r? Frozen? Nuts. I see your messages. Okay, there we go. So I'll let you guys catch up, but if you think of the limits for R, shout them out. Yeah, 0 to 4. Good. Okay, now to do surface area, we need the differential for surface area. So ds, capital S, that's the surface area differential. Okay, so let's see, we said this would be RU, this would be capital R, RU cross capital RV, and then we would do du dv. That would be sort of the formula, but of course our variables are a little different. So our independent variables here are little r and theta. So we'll do little r for radius and theta, and instead of du dv, we'll do dr d theta. Oops. Okay. And now we have some work to do. So we have to do some partial derivatives. Partial of r with respect to little r would be cos theta, 2r, and sine theta. Any questions about that one? And then r with respect to theta. Okay, so now we're going to do derivative of cos, so that'll be negative r sine theta. And with respect to theta, r squared goes to 0. And then r cos theta. Okay. Okay, any questions? Putting some barbs over the vectors that got neglected here. All right, so now we have to do this crazy cross product. So r with respect to r cross r with respect to theta. Okay, any questions? I hope this comes out nicely. Okay, here we go. So for the I component, looks like we're going to have 2 r squared cos theta minus 0. So just 2 r squared cos theta. And then, oops, and then minus the j component. So with that, we're going to go this way, right? So it looks like we're going to have r cosine squared plus r sine squared. Double negative will make a positive. R cos squared theta plus r sine squared theta. Okay. Any questions? I'm trying to make space real quick here, so just one second. I think we're all right. Okay, so the K component, to me, I think, is it 2r square sine theta? Right, how's that? Of course, that simplifies. So here goes. This is going to be, is a vector, 2r squared cos theta, comma, is that just negative r in the middle here? And then a 2r squared sine theta, like that. Okay, any questions? We need the magnitude of this. If now magnitudes of these vectors that are cross products, the magnitude becomes an area. So magnitude of r with respect to r cross r with respect to theta is what we're working on now. Okay, so this should be fun. So we're going to have a 4 r to the 4th. I think I'll group these because we're going to have a cosine square theta and a sine square theta. And then there'll be plus an r squared there, right? Did I lose? No, I got the 4s. Yeah, that's cool. Okay, so I guess we could factor that. So you'd have an r squared here. Actually, let's do it. Yeah. So there's an r squared, and then there'll be a 4r squared plus 1. Like that. And the point is to factor that. So when you bring in square root of a square, that's absolute value. So technically, you'd say absolute value of r times the square root of 4r squared plus 1. Okay. Okay, but reminding ourselves that r is between 0 and 4. We don't need the absolute values. And you can say this is equal to just r times the square root of 4r squared plus 1. So that's the cross product that will give area. Technically, this thing is sort of a Jacobian, but I'm not going to go into the details on that. When we do our double integral of ds over our surface, and again, I'm naming the surface S, that's generally what we call it. Okay, so S is the surface's name. And so when we're just saying you add up the differential pieces of S all over S, that's what that says. Okay, and of course the formula says, well, this is a double integral of the magnitude of r, oops, hang on, r, little r with respect to r cross r with respect to theta, and then that'll be a dr d theta. And now I can put limits. So r, I think, was going from 0 to 4, and theta from 0 to 2 pi. And so we're going to integral 0 to 2 pi, integral 0 to 4 of r square root of 4r squared plus 1 dr d theta. you could almost split that in, not almost, you could split that into two integrals that are multiplied. So the first integral, and by the way, I'm going to do a substitution. So kind of obvious here that u is going to be 4r squared plus 1. And what, so du is 8r dr. So we'll have to do 1/8 du is r dr. Okay, so maybe I'll do this in a couple of steps. So first one, I've got the 0 to 2 pi. Then I've got another integral with 1/8. I'm just going to have the square root of du, I think. And then we'll have our d theta. U goes from where to where? Let's see. Well, when r is 0, u is 1 here, so that's the lower limit I need. And when r is 4, you're doing 4r squared, so that's 4 times 16, which is 64, plus 1. I think that's 65. That's not nice. Okay. 1 to 65. Okay, so, you know, maybe just to show you we can, put the 1/8 back here, you really could just make this two integrals 0 to 2 pi d theta, because the limits are constant. And then you got the u to the half from 1 to 65. Okay, so I've got the 1/8, I got the 2 pi, I've got a 2/3 u to the 3/2 from 1 to 65, I think. Times 6, 4 goes into 8. 2 times 6, is it 1/6? So could I say pi over 6 times 65 to the 3/2 minus just 1 to the 3/2, which is 1. And then I'm not going to do any more with that. I did evaluate it. It comes out to, I didn't actually, never mind. That simplifies. You could write this as pi over 6. I don't want the approximate equal there. You can simplify this as pi over 6, and you could write this as 65 square roots of 65 minus 1. So if you want to do that. Okay, so that's that. So that's a surface integral, but it's just a surface area. It's the simplest kind of a surface integral. And I guess I should do one more thing. How are we doing for time? 7:23. Yeah, let's do one more thing. Everybody okay out there? Okay, so I wanted to do a real quick development of what happens when z is a function of x and y. So just real quick, this is theoretical. So if z is some f of xy, then let's just say the parameterization is, again, we've said already x will just be x, y can just be y, and z is f of xy. So my position vector is r as a function of x and y. So x is x, y is y, but z is f of xy. Okay, so that's one way of doing it. I don't even need to use a U or a V or anything like that. Okay, any questions? All right, now I want to go ahead and do ds as a vector and a scalar. So ds, the vector, is going to be Rx cross Ry. So you just do both partial derivatives and do the cross product, and then I'll have a dy dx like that. So you can call that dA if you like. Now I was referring to this thing as sort of a Jacobian. It is. But I'll just let that ride for now. So Rx cross Ry. Let's go ahead and do the Rx here. Rx would be 1, 0, fx, okay? Just doing this function. And then Ry would be the derivative of x is 0, of y is 1, and then you have an fy. Okay. And then maybe over this side we can squeeze in a cross product here. So Rx cross Ry is what I want for the differential. Okay, so here goes. I'm going to have a 1, 0, fx, 0, 1, fy, and then the ijk's. Okay. And the I gets 0 times fy minus 1 times fx. So I think it's just negative fx. I gotta think about that. I think it's okay. Then minus j gets the 1 times fy minus 0 fx. So this just gets an fy. Okay. And then plus k gets the 1 times 1 minus 0 times 0. So it's just k times 1. So this vector differential is negative fx, negative fy, and then just 1 for the z coordinate. So ds is equal to negative fx, negative fy, 1. Dy dx we'll just call dA. I sort of want to do a little bit of a picture here. I want that parallelogram, but I also want that unit normal. So I'm just going to have to do that on the next page, I guess. So I've got my surface here like that. And I've got my 2 tangent vectors kind of going like this and like this. So that might be fx here. Sorry, no. That's rx, my bad. So that's like rx here. And down here is ry. And I probably want to change the order of those. So forgive me while I'm going to do ry pointing to the... So I'm trying to think about my right-hand rule. Yeah, so I'll do rx. It doesn't matter. Rx to the right, ry out. And then I'm going to have ds going up this way. Okay. And I've got it pointing up. It's an upward normal because the z component is positive. So this is upward. coming up from the surface, but it's not pointing straight up. It's normal to the surface. So I'm actually going to tweak that a little bit so that it doesn't look like it's coming straight up. So I'm gonna have to go this way kind of. Okay. So that's an upward normal. Okay. And that's going to be important. Sometimes we want these ds differentials to point down. Okay, so just to make a comment here, if we want a downward normal, we can just change the sign of this. So we would, for that case, we would do ds would have just fx, fy, and a -1 dx. So that's a downward normal. Okay. Either way, just remember ds, which is the surface area differential. This is the magnitude of ds, the vector. Okay, and of course this would just be the square root of fx squared plus fy squared plus 1 dx. Okay, and then the only purpose of pointing that out is to sort of take you back. So now I'm going to fly back to double integrals. Okay, so here's 15.5 when we were covering surface area the first time as an application of the double integral. You know, we did a completely different development, but there's our ds again right here. So this is the same, okay, as what we just developed using parametric surface development, but it's the same computation in the end. All right, so let's go ahead and we're long overdue for our break, so let's take our 10-minute break. And I'll see you guys in a little bit. And just wanted to go back. I was using the wrong syntax on GeoGebra. So I just, maybe I thought I'd show you, for instance, we had done a cylinder at one point. Let's see if I can find that. Okay, so the cylinder was this one. A cos theta, A sine theta, and then Z, where A is just the radius of the cylinder and Z can range however it wants. I think I'll use a U for theta, and I don't mind letting Z be Z. So just real quickly, I wanted to jump into GeoGebra, and you can see I was playing around with this already, but just to walk you through it, I would just do GeoGebra 3D again. And the funny thing that I misunderstood is that you don't put the vector in brackets. You just list it. You just list the x, y, and z coordinates separated by commas. So the command is just surface. So you just type surface like that, and then in parentheses, you just start by giving first the x coordinate, and I think we said x is like r cos theta. I'll do a cylinder whose radius is 2, so we would do 2, and then the cos of an angle, and you can use whatever letter you want. I think I said I would use u for theta. And then, so that's the x coordinate, and then a comma, and then the y coordinate was 2 sine u. Oops. So 2 sine of u, and now another comma, and then the third coordinate was just z, like that. So you've got the x, the y, both of those, x and y are on circles of radius 2. You should recognize that as the parameterization of a circle. But then we're letting z just vary independently. But then you have to give ranges for the u, which is my theta. So I'm going to say u should range from 0 to 2 pi. So in GeoGebra, see how I wrote that? I just wrote comma u, comma 0, comma 2 pi. Those are the limits for u. And then v, I'm going to have 0. I'm just going to have my z, I should say, is going to go from 0 to 4. So I'm going to say z, comma 0, comma 4. And so that's just handled natively in GeoGebra. You don't have to do anything special to do a parameterization like this. And you can do multiple parameterizations in the same graph. Okay. So is there any question about that? I feel like I want to get redeemed on my sphere. So I don't know, I couldn't edit these well. But so I think I'm just going to refresh the page and dump my last graph. And again, type the surface command. And in parentheses, the x coordinate on a sphere is radius times sine phi cos theta. So I'm going to do a radius 6, and then I'll do sine. I think 6 is too big. I think I'm looking at the coordinate system. I think I'll do a radius of 4. So 4. It's sine phi cos theta. So sine, I was using v for phi because it rhymes. And then cos of u for theta. Okay, so that's my x coordinate. Then a comma, the y coordinate would be 4 sine phi sine theta. So sine v and sine theta, which is my u. Okay, and then the z coordinate was cos phi, so that'll be cos of v. And now you don't make this into a vector. All I did was list each individual component for the sphere. And then it needs limits for phi and theta. Again, phi is my v. So I need v to go from 0 to pi, and I separate all those with commas. And then theta is my u, so I needed u to go from 0 to 2 pi. 0, 2 pi. And if I, hey, that's beautiful. It's a pancake. And it's done that because my scaling is a little off. Okay, and I'm not sure initially how to change the scaling on an iPad. Maybe there's a problem. Oh, I didn't do 4, I see. So I need to put a 4 in front of the z coordinate, so I'm going to go out and change that. Should be 4 cos phi, and that'll scale it up better. And let's see if I hit enter. That's better. So that's a lovely sphere in GeoGebra. And I say that works pretty good. You just got to type surface, list the x, y, z coordinates, and give lower limits and upper limits. So let's put that in to the notes in case you want to do one of these. Okay, so real quickly, I'm going to pop over. How about if I squeeze it in? I'm going to put it right here. So GeoGebra 3D. Okay, let's say your function is r of uv. And let's have that be, as I said before, x of uv, y of uv, z of uv, like that. There would be limits on u. So let's say a to b for u, and c to d for v. Okay, and then in GeoGebra, you would just type. Let's just write. How about if I say the syntax? You would just type surface, and it doesn't have to be capital S. So you would say surface, you list your x of uv, your y of uv, your z of uv, and then you give the limits on u. You would just say u, comma a, comma b, and then v, comma c, comma d, and that'll graph your surface. And it works better on a computer that has a regular keyboard and a mouse, I think, than a tablet. But you can be done. I'm doing it on a tablet right now. Okay, any questions about the GeoGebra graph? Just looking at my chat, if you have any